The fault in the power system is defined as the defect in the power system due to which the current is distracted from the intended path. The fault creates an abnormal condition which reduces the insulation strength between the conductors. The reduction in insulation causes excessive damage to the system. The fault in the power system is mainly categorized into two types. They are 1. Open circuit fault. 2. Short circuit fault. The different types of power system fault are shown in figure. Type of faults. Faults in power systems are divided into open circuit, also called series faults, and short circuit, also called shunt faults. Faults shall stimulate the switching of the protection devices. Therefore, faults occur at the terminals of either active or passive electrical equipment. Active electrical equipments include synchronous and asynchronous machines or grid equivalents. Passive electrical equipment includes transformers, transmission lines, or loads. Open circuit faults are characterized by an increase in voltage and frequency and a decrease in current in the faulted phase. Therefore, they can be detected by monitoring the voltage of each phase. If the voltage value rises, it means that an open circuit fault happened. Open circuit faults cause cessation of current flow, and they rarely occur. The faults in the power system may occur because of the number of natural disturbances like lightning, high-speed winds, earthquake, etc. It may also occur because of some accidents like falling off a tree, vehicle colliding with supporting structure, aeroplane crashing, etc. Open circuit fault. The open circuit fault mainly occurs because of the failure of one or two conductors. The open circuit fault takes place in series with the line, and because of this, it is also called the series fault. Such types of faults affect the reliability of the system. The open circuit fault is categorized as open conductor fault, 2 conductors open fault, 3 conductors open fault. The open circuit fault is shown in figure. Short circuit faults. Whenever there is a short circuit fault, the voltage and frequency will decrease while the current will increase in the faulted phase. Accordingly, they can be detected by the observation of the current of each phase. If there is an increase in the current value, it highlights the initialization of a short circuit fault. Short circuit faults are the most hazardous as the current is increased to a lot more, e.g. 10 times more than the nominal current of the instrumentation. Short circuit fault may take an arc form on overhead transmission lines, causing the conductor to burn and break if not timely cleared. Short circuit faults may also turn the faulted phase into loads in interconnected systems, and that is because of the large decrease in voltage and frequency in those faulted phases. Accordingly, induction and synchronous motors may feed the fault during a short circuit fault, which worsens the situation even more. Shorts are commonly occurring, and there are two main types of short circuit faults, namely symmetrical faults and unsymmetrical faults. Symmetrical faults. A symmetrical fault is balanced and it affects all phases equally, meaning the voltage drops of all the 3 phases is equal and has the same magnitude, which is proportional to the severity of the faults. A symmetrical fault is the most severe because it involves all 3 phases, and roughly 5% of faults involved in a 3-phase system are symmetrical. Asymmetrical faults. An asymmetrical fault is unbalanced and it affects each phase separately, meaning the voltage drop of each phase is uneven and has different magnitude depending on the nature of the fault. An asymmetrical fault can occur as a line-to-ground LG fault, line-to-line LL fault, or double line-to-ground LLG fault. Asymmetrical faults are difficult to analyze, and almost 95% of faults involved in a 3-phase system are asymmetrical. The subsections below will provide additional details about the types of asymmetrical faults. Line-to-ground fault. A line-to-ground LG fault is caused by a conductor making contact with a grounded structure, and it is the most common. 70% of the entire faults are found to be LG faults. The LG faults depicted causes IB equals 0, IC equals 0, and VA equals 0. Line-to-line fault. If one phase touches another phase, it causes a line-to-line LL fault. About 15% of all faults are found in LL faults. The LL fault depicted causes IB equals 0, IC equals 0, VB equals 0, and VC equals 0. Double line-to-ground fault. When 2 phases come in contact with the ground, it leads to a double line-to-ground LLG fault. 10% of all faults fall under this type. The LLG fault that is depicted causes IA equals 0, VB equals 0 and VC equals 0. Unsymmetrical fault. The fault gives rise to unsymmetrical current. I.E. current differing in magnitude in phases in the three phases of the power system are known as the unsymmetrical fault. It is also defined as the fault which involves the one or two phases such as LG, LL, LLG fault. The unsymmetrical makes the system unbalanced. It is mainly classified into three types. They are 1. Single line to ground LG fault. 2. Line to line fault LL. 3. Double line to ground LLG fault. The unsymmetrical fault is the most common types of fault occur in the power system. Single line to line ground fault. The single line of ground fault occurs when one conductor falls to the ground or contact the neutral conductor. The 70 to 80% of the fault in the power system is the single line to ground fault. Line to line fault. A line to line fault occurs when two conductors are short-circuited. The major cause of this type of fault is the heavy wind. The heavy wind swinging the line conductors which may touch together and hence cause short circuit. The percentage of such type of faults is approximately 15 to 20%. Double line to line ground fault. In double line to ground fault, the two lines come in contact with each other along with the ground. The probability of such types of faults is nearly 10%. Causes and effects of types of faults. These faults can be caused because of the circuit malfunctioning as well as broken conductor in one phase or more phases. The effects of open circuit faults include the following. Electrical power system irregular operation. These faults may danger to animals as well as human beings. In particular, a portion of the network, when the voltage is exceeded beyond normal values, then it causes insulation failures and develops short circuit faults. Even though these types of circuit faults can be accepted for a long time as compared with short circuit type faults, because these faults must be detached to decrease the high damage. Fault types. A power failure in the power network is classified as a shunt fault, short circuit fault, or a series fault, open circuit fault as told earlier. An open circuit fault occurs when one or more conductors' phase is open in the system due to a broken line. The short circuit fault occurs when two or more conductor lines come into contact with each other or to the ground. 75 to 80% of power failures are either a line to ground short circuit or a transient fault. Moreover, short circuit faults are classified as symmetrical faults, balanced faults, or as unsymmetrical faults, unbalanced faults. Short circuit faults mainly occur because of failure within insulation among phase conductors in earth. An insulation failure can cause a short circuit path formation that activates short circuit conditions within the circuit. The definition of a short circuit is an abnormal connection of extremely less impedance among 2 points of dissimilar potential, whether completed by chance or purposely. These faults are the most common types, which result in the abnormal high current flow throughout the transmission lines or equipment. If short circuit faults are allowed to continue even for a small time, then it leads to wide harm to the apparatus. Short circuit faults are also known as shunt faults because these faults mainly occur because of the failure in insulation among phase conductors, otherwise among phase conductors in earth. The different achievable short circuit fault conditions mainly comprise 3 phases to earth, 3 phase clear of the earth, single phase to earth, phase to phase, 2 phase to earth, phase to phase, and single phase to earth. Both the 3-phase fault clear of the earth, as well as the 3-phase fault toward earth, can be symmetrical or balanced, while other faults are unsymmetrical faults. Causes and effects of short circuit faults. The short circuit faults may occur because of the following reasons. These faults may occur because of the internal, otherwise external effects. Internal effects are transmission lines breakdown, equipment damage, insulation aging, corrosion of insulation within the generator, improper installations of electrical devices, transformers, and their inadequate design. These faults can be occurred because of outside effects of apparatus, insulation failure because of lighting surges, and mechanical damage by the public. The effects of short circuit faults include the following. Arcing faults can cause fire and blast in apparatus like transformers as well as circuit breakers. The flow of power can be restricted severely, otherwise even totally blocked, if the short circuit error persists. The system operating voltages can go above or below their acceptance values to make a damaging effect on the service provided through the power system. Because of abnormal currents, the apparatus gets heated so that the lifespan of their insulation can be reduced. Causes of types of faults. The main reasons to cause electrical faults include the following. Weather conditions. It includes lightning strikes, heavy rains, heavy winds, salt deposition on overhead lines and conductors, snow and ice accumulation on transmission lines, etc. These environmental conditions interrupt the power supply and also damage electrical installations. Equipment failures. Various electrical equipment like generators, motors, transformers, reactors, switching devices, etc. causes short-circuit faults due to malfunctioning, aging, insulation failure of cables, and winding. These failures result in high current to flow through the devices or equipment, which further damages it. Human errors. Electrical faults are also caused due to human errors such as selecting improper rating of equipment or devices, forgetting metallic or electrical conducting parts after servicing or maintenance, switching the circuit while it is under servicing, etc. Smoke of fires. Ionization of air, due to smoke particles surrounding the overhead lines, results in spark between the lines or between conductors to the insulator. This flashover causes insulators to lose their insulating capacity due to high voltages. Types of faults and their effects. The effects of electrical faults mainly occur because of the following reasons. Overcurrent flow. When the fault occurs, it creates a very low impedance path for the current flow. This results in a very high current being drawn from the supply, causing the tripping of relays, damaging insulation and components of the equipment. Danger to operating personnel. Fault occurrence can also cause shocks to individuals. The severity of the shock depends on the current and voltage at the fault location and even may lead to death. Loss of equipment. Heavy current due to short-circuit faults results in the components being burnt completely, which leads to improper working of equipment or device. Sometimes heavy fire causes complete burnout of the equipment. Disturbs interconnected active circuits. Faults not only affect the location at which they occur but also disturb the active interconnected circuits to the faulted line. Electrical fires. Short circuit causes flashovers and sparks due to the ionization of air between two conducting paths, which further leads to fire, as we often observe in news such as building and shopping complex fires. Fault limiting devices. It is possible to minimize causes like human errors, but not environmental changes. Fault clearing is a crucial task in the power system network. If we manage to disrupt or break the circuit when a fault arises, it reduces the considerable damage to the equipment and also property. Some of these fault-limiting devices include fuses, circuit breakers, relays are discussed below. Fuse. It is the primary protection device. It is a thin wire enclosed in a casing or glass which connects two metal parts. This wire melts when excessive current flows in the circuit. The type of fuse depends on the voltage at which it is to operate. Manual replacement of wire is necessary once at a blowout. Circuit breaker. It makes the circuit at normal as well as breaks at abnormal conditions. It causes automatic tripping of the circuit when a fault occurs. It can be electromechanical circuit breakers like vacuum, oil circuit breakers, etc., or ultra-fast electronic circuit breakers. Relay. It is a condition-based operating switch. It consists of a magnetic coil and normally open and closed contacts. Fault occurrence raises the current which energizes the relay coil, resulting in the contacts to operate so the circuit is interrupted from flowing of current. Protective relays are of different types like impedance relays, Mo relays, etc. Lighting power protection devices. These include lighting arresters and grounding devices to protect the system against lightning and surge voltages. Application-based three-phase fault analysis. We can analyze three-phase faults by using a simple circuit as shown below. In this, temporary and permanent faults are created by fault switches. If we press the button once as a temporary fault, the timer's arrangement trips the load and also restores the power supply back to the load. If we press on this button for a particular time as a permanent fault, this system completely shutdowns the load by relay arrangement. How to detect and locate the faults. In transmission lines, the fault is very easy to identify as the crisis is generally noticeable. For instance, once any tree has fallen over the transmission line, otherwise, an electrical pole can be damaged as well as the conductors are lying on the earth. In a cable system, fault locating can be done when the circuit is not worked, otherwise when the circuit works. There are different methods for fault location which can be divided into terminal techniques, which work with currents as well as voltages measured at the cable ends, and tracer methods which need inspection through the cable. The normal area of the faults can be located at the terminal techniques to speed up tracing over a transmission cable. In wiring systems, the location of the fault can be found throughout the verification of the wires. In difficult wiring systems, wherever the wires may be buried, these faults are placed through a time domain reflectometer that sends a pulse down the wire and after that examines the reflected signal to recognize faults in the electrical wire. In a famous underwater telegraph cable, responsive galvanometers were utilized to compute fault currents through testing at fault cable ends. In cables, two methods are used to locate faults, like the Varley loop as well as Murray loop. In a power cable, an insulation fault cannot occur at low voltages. So, a thumper test is used by applying a high voltage pulse, high energy to the cable. The fault location can be done by listening to the discharge sound at the error. When this test donates to harm at the site of cable, it is useful as the faulted location would have to be re-insulate once set up in any case. In a distribution system with high resistance grounded, a feeder can expand an error to earth, however the system maintains in process. The faulted as well as energized feeder can be found in a ring-type current transformer which gathers all the phase wires for the circuit. Simply the circuit includes a fault to earth will illustrate a net disturbed current. The grounding resistor is used to make the current of the earth fault easier to notice among two values to beat the fault current. Impact of renewables on the grid. Ensuring the reliability and stability of a smart grid system involves considering various factors. One key aspect is integrating renewable energy resources (RERs) into the power grid. When RERs are incorporated at a low voltage level, it increases the likelihood of faults due to bidirectional power flow. The location of RERs in the system also plays a crucial role, influencing dispatch modes based on penetration levels and their rapid response. Additionally, fluctuations in current and voltage, caused by variations in active and reactive power due to RERs, impact the overall stability and reliability of the system. The topology of inverters associated with RERs is another factor influencing the system's reliability. Control parameters, including gains of real and reactive power, can alter the damping ratio of RERs, impacting system oscillations. Furthermore, frequency deviation occurs during post-fault conditions when the smart grid system transitions from grid-connected to island mode. This frequency deviation can lead to generator tripping, resulting in dropped loads. Continuity of electric power supply is essential, therefore, issues that might cause a loss of a generation unit are unsolicited. The purpose of preventing a generation unit loss using FRT techniques is as much as economically important as it is technically. A voltage time or frequency time diagram called the FRT diagram is used to demonstrate the essential requirements a generation unit shall meet to ride through a voltage or frequency disturbance. The FRT diagram may be different among countries as the grid codes differ. During a fault, the grid code requires the generation unit to stay connected to the grid within a certain range of voltage and frequency. Accordingly, the setting of the protection devices strongly relies on FRT requirements, which may require the generation units to generate maximum reactive power without violating the transient rating limits. The parameters involved in defining the FRT requirements include the follow: network design, generator type, Gault type and amplitude, commonly short-circuit faults, fault occurrence impedance, fault clearance period, power control procedure. The effects of the symmetrical and asymmetrical short-circuit faults on the three-phase voltage magnitudes vary. Consequently, they affect requirement of the FRT differently. Furthermore, the location of the generation units and other components is crucial in the application of the FRT. Voltage ride-through during a fault, changes will occur to the system's voltage, current, and frequency, which can lead to the disconnection of some generation units from the grid. This reduces the reliability of the power system. Therefore, TSOs, in presence of high integration of REN sources, require generation units to have LVRT capabilities or even ZVRT capabilities. In some cases, TSOs will require HVRT capability as well. A LVRT capability curve is displayed. The voltage of a generation unit operating in normal condition Vn is as demonstrated in area during a symmetrical fault or an asymmetrical LL or LLG fault, which occurs at the time interval t0, the generating unit experiences a voltage sag. The LVRT allows the generating unit to remain connected to the grid by withstanding the voltage drop for a certain time represented in area B. When the voltage level reaches at area C, the generating unit should disconnect from the power system. The voltage is regulated back to VR when the fault is cleared after T2. This LVRT capability ensures fast post-fault recovery and stability for the system. Furthermore, the occurrence of asymmetrical LG fault causes a voltage swell. When a voltage swell occurs, the generating withstands this condition through a HVRT capability. A HVRT capability curve is displayed.